Last time we gave the definition of a function and we looked at some examples. Here I have one of those examples. We said that this map H was a function where we sent 7 to 0, 3 and 2 to 1, and 4 to 9. We called this set the domain and this set the range. We can write out the domain in set notation. The domain here is 2, 3, 4, and 7. That is all of the numbers in this set. The range is all the numbers in this set. And it doesn't really matter what order you put them in. I'm just going to put them in lower to higher order. So this is the range. We also said in the last video that we can represent a function by using arrows. So here we had that 7 was being sent to 0. 3 and 2 are both being sent to 1. And the number 4 is being sent to 9. And although we don't have the number 5 with these arrows on the side, as you can see it was left out, it's still in the range. So it is a number in the range. We also mentioned that we could write this map as an ordered pair. So 7, 0, 3, 1, 2, 1, and 4, 9. So the next thing I'm going to do is I'm going to give you some ordered pairs, and I want to know if it defines a function. So can you take the x-coordinate and put it in a set, and then call that set the domain, and the y-coordinates in another set, and it's the range. And we want to see if we have a function. So every x element is only being mapped to one element in the range. And how you're going to be able to tell is you just have to see if you have a repeating x-coordinate. Let's look at an example. So let's say we have the following sets of points: 1, 1, 2, 3, and 4, 9. So do these ordered points represent a function? So when we see these ordered points, what we want to think about is that we have in the domain, so I'm going to just say D for domain and R for range, we have the points 1, 2, and 4. And in the range, we have the points 1, 3, and 9. In fact, we can write domain over here and say the domain is 1, 2, and 4, and the range is 1, 3, and 9. And yeah, we could have more points in the range, but like for the last example, but that we don't have enough information for that. So we're just going to use the points they give us and assume that the points that they give us define the domain and the range, unless we have more information like a picture. But if I just give you points, you're going to have to use the x-coordinates as the domain and the y-coordinates for the range. Okay, in this picture we have 1 being mapped to 1, 2 being mapped to 3, and 4 being mapped to 9. You can obviously see that this is a function. So the answer is yes, it is a function. What about 2, 3 and 4, 3? Is this a function? Does this represent a function? Well, notice that I repeated the y-coordinate. Is that okay? Well, remember that the y-coordinate is in the range, and we said that we can repeat numbers in the range. If I wanted to draw a picture, what I have here is 2, 4, and then the number 3. And 2 of these numbers in the domain, well, the only 2 we got, they're both being sent to the number 3. And the rule for a function was every element is being sent to exactly one element in the range. And you can see that that's true. 2 is not being sent to two different things, and 4 is not being sent to two different things. So this is a function. If I change this a little bit, so let's say I have 2, 1, 1, 4, -1, 6, and 2, 8. Would this represent a function? So do these ordered pairs represent a function? The answer here is no. Can you look at it and tell me why it's no? Well, the answer is we repeat x coordinates. Again, if we draw a picture, we put all the x coordinates in the domain, so 2, -1, and 1. And then we put all of the y coordinates in the range, so 1, 4, 6, and 8. You'll see that we have 2 being sent to 1, 1 being sent to 4, -1 being sent to 6, and 2 being sent to 8. So this number 2 is being sent to 2 numbers in the range. And remember, every number in the domain has to be sent to exactly one element in the range. So whenever you repeat x coordinates, then it's not a function. I'm going to write out the domain in set notation, just so that you've seen it before, so you'll be able to say you've seen it. 2, 1, -1, that's the domain, that's all of the x coordinates, and the range is 1, 4, 6, and 8. All of the y coordinates. Okay, the next thing we're going to do is we're going to look at equations and try to figure out if they represent functions. So is the following equation a function? And the equation I'm going to give you is y is equal to x plus 1. So when we have an equation like this, where the y is dependent on the x, we're always going to let the numbers that can be plugged in for x, we're going to let that be the domain. So that set of numbers is the domain, and the set of numbers you get when you plug in an x, which is going to equal y, that's going to be your range. I'm going to graph this. The y-intercept here is 0, 1, because if I plug in 0, I get 1. And the slope is 1, so we go up 1 over 1. So the graph of this equation looks like this. So how can we figure out if this is a function? Again, I'm going to write down here the set of numbers that we can plug in for x is the domain. And the set of numbers we can plug in for y So I'm going to rephrase that. The set of numbers we get after we plug in a number for x, it's the set of numbers for y, we get after we plug in a number for x is the range. So what I'm saying here is you're going to plug something in for x, and whatever you plug in is going to determine what your y value is. So if you have a certain number of elements you can plug in for x, that will determine the elements you get for y. So your y depends on x. So that's how we're going to figure out the domain and range. And we're going to talk about that later. Like what's the domain for x and what's the range for y. Right here, you can look at the picture. You know that for x, you could plug anything in that you want. You could plug in 7 and you're going to get 8 for y. You can plug in -5 for x and you're going to get -4 for y. Just plug in this number, add 1, that will give you y. In fact, any number you choose for x, you're going to get a y value. The domain here for x is all real numbers. In fact, we can say the domain is from -infinity to infinity. We'll talk about this more in the next video, but we can write this in interval notation as -infinity to infinity. So the domain, let me phrase it this way, maybe this will be the best way to say it. The domain is all real numbers. I can plug any real number that I want to in for x. Okay. The range is also going to be all real numbers, because if you plug any number in for the domain, you're going to get a number for y, the range. So if you wanted the number 5 for the range, well, that means you plug in 4 for x, and then you would get 5. So any real number you can think of, let's say you put a -1 million here. Well, if you plug in -1,000,001 into this, you'll get that number. So you will get all real numbers for the range. And you can see this by looking at the graph. So this graph tells you that for any x you choose, you're going to get a y. And we're going to cover every single point on this y-axis. If you went up to 100, well, if you drew a line like this line is going to cross it. So that 100 is going to be counted. So any number you choose for y, let's say you have -1 million, this line is going to go down forever. And so eventually it will cross this -1 million mark. So the domain and range are all real numbers. But let's figure out if this is a function. So for it to be a function, every x value that you plug in is only going to be sent to one y value. Is that the case for this equation? And the answer is yes. If I plug in 1, I'm going to be sent to 2. I'm only going to be sent to 2. I'm not going to be sent to anything else. If I plug in the number 10, I'm going to be sent to 11. I'm not going to be sent to 2 different numbers here. So the answer is yes, this is a function. So yes. Let's look at an example where we get something that's not a function. X squared plus y squared is equal to 1. This is not a function. I'm going to write it as a question. Is this a function? But I'm going to go ahead and tell you it's no. Why is it not a function? Well, first off, what is this the graph of? We know that this is the graph of a circle. Its center is 0, 0, and it has a radius of 1. So we can just sketch this graph. Looks something like that. Now, what is the rule for something to be a function? Every x value is sent to exactly one y value. What happens if we plug in, for example, x is equal to, let's plug in 0. If I plug in 0, I get 0 squared plus y squared is equal to 1. So y squared is equal to 1, which tells me y is equal to plus minus 1. So when you plug in 0, you get two options for y. You can have a plus 1, which corresponds to this point right here. See, this is 0, 0. If I add 1, I'll get the point 0, 1 here. And I have the point 0, negative 1, which is right here, 0, negative 1. So you can see that I have two y values for one x value, and that's not good. I have x being, well, x when x is 0 is being sent to 1, and it's also being sent to negative 1. When that happens, it's not a function, so no. Another way you can tell is by looking at the graph. We have something called the vertical line test, which says if you draw a vertical line through this graph, so a vertical line being very straight up and down, if it hits the graph more than once, here I'm hitting it twice, then it's not a function. For the one we did just a minute ago, notice if I draw a vertical line anywhere that I want to, I'm always going to hit this graph exactly one time. So if that happens, then it is a function. If it hits the graph more than once, then it's not a function, because I'm having an x value sent to two y values. Another way to tell without even graphing the function, here we knew what the graph looked like, and the last one we knew what the graph looked like because we've done this in the last chapter. But another way to tell is to look at the equation and see what the power is on y. If the power is an even number, then it's not a function, okay? So power is even. So even powers on y means it's not a function. So if I have a 2, a 4, a 6, a 8, a 10, anything like that, then it's not a function. It actually doesn't matter what the power is right here for this x. Okay, let me give you another example. Let's say I have y is equal to x squared. Now we did this problem before, we graphed it. The graph actually was called a parabola, and it looked like this. And how we graphed it was we plotted points. We said that 0, 0 was on the graph. If we plug in negative 1 into x, we square it, we get 1 here. If we plug in 1, we get 1, and so on. Here, you can see that if I draw a vertical line through this, no matter where I draw it, it's only going to hit the graph once. So it passes the vertical line test, which means it's a function. But also, looking at this, you can see that I don't have any squares or anything on the y, so that means it's a function. Again, you can also plug in values for x. So as long as whatever you plug in, you only get sent to one y value. So I plugged in 0, I was sent to 0. I plugged in negative 1, I'm only going to be sent to 1. Yes, I have two numbers being mapped to the same y coordinate, but that's not a problem. A problem with a function when you don't have a function is that when you have one of the x coordinates being sent to two y coordinates. But there's no way for that to happen with this particular problem. If I switch this, if I said x was equal to y squared, then this is not a function. Because you can see if y is equal to 1, well, x is 1, right? So y squared is equal to 1. But if I plug in -1 for y, I also get 1 for x. So you can see that 1 is being sent to 1 and 1 is being sent to -1. This is not a function. Also, if you were to graph this, I don't expect you to know what this looks like, but I could give you the graph and I could ask you if it's a function or not. Turns out it looks like this. It looks almost identical to this one. It's just flipped, rotated 90 degrees clockwise. And if you draw a vertical line through it, it's going to pass more than once through the graph. So you would have something that's not a function. All right, we're going to move on. The next thing we're going to talk about is how to evaluate functions at particular numbers. So we're going to discuss something called functional notation. And that's when we use f of x instead of y. Or you could use g of x, h of x, anything like this, I of x, k of x. You're going to have a letter, parentheses, x, parentheses. You're going to be using this kind of notation instead of the letter y. And the reason we do this is because sometimes we're going to talk about several functions, like if we have y is equal to x squared plus 3, and also y is equal to 5x minus 1. When you have more than one function, you don't want to call both of them y, because you won't know which y you're referring to. So what we're going to do instead is say, oh, this one's f of x and this one is g of x. Now you heard me pronounce it, but I'm going to write it down how we pronounce this. So f of x, we say f of x. That's what you're going to hear me say 99% of the time. But what it means is the value of f at x. So we're plugging in a particular x value and we're going to get our y value, which is the value of f. Okay, let's look at some examples. Here's the first one. We're going to let f of x be equal to 3x plus 1. This is a function. 3x plus 1 is a line with a slope of 1 and a y-intercept of 0, 1. I want to find the following. F of 2, f of -4, and f of x plus 2. Tell you what this means. You see how x is our domain and our range is going to be whatever we plug in for x, what we're going to spit out for y, which is going to be the value of f. So what this is saying is I want you to plug in 2 wherever you see an x. Let's do this in blue. So let's look at our function, which is 3x plus 1. I see an x here and I'm going to put 2. So this is 6 plus 1, which is 7. So that tells me f of 2, or the value of f at 2, is equal to 7. In other words, when I plug in 2 into this function, I get 7. 2 is being mapped to 7. How about the next one? Plug in -4. So 3 times negative 4 plus 1. Well, this is negative 12 plus 1, which is negative 11. This one's a little bit harder. Wherever you see an x, this is saying plug in x plus 2. So this is 3 times x plus 2 plus 1. I'm just plugging it in right here. Whatever's here goes here. So I'm going to distribute this 3. I get 3x plus 6 plus 1, which means this is 3x plus 7. So f of x plus 2 is 3x plus 7. Let's do another one. Let g of x be equal to 7 minus 3x. Find the following. G of 0, G of 7/3. Let's do G of S, and let's plug in G of 3 minus x. In fact, let's put a y here. Okay, G of 0 means I just plug in 0 for x. So I get 7 minus 3 times 0, which is 7 minus 0, which is 7. G of 7/3 is 7 minus 3 times 7 over 3. Remember, the 3's cancel, and I get 7 minus 7, which is 0. G of S, now this might be a little confusing, but just follow the rule. Whatever's here goes here. So here's an S, so I'm just going to put an S there. So this is 7 minus 3s. What is G of 3 minus y? Well, we have 7 minus 3 times 3 minus y. So this is 7 minus, distribute this negative 3 to everything, and we get minus 9 plus 3y. And combine like terms, 3y minus 2.